Hello and welcome to Empowered Learning. This video will talk about what it means to have a determinant of a matrix, and as well as using determinants in an application for solving systems of linear equations by what's called Cramer's rule. So the first thing that I want to talk about is what is actually a determinant. And so depending upon the order or the dimensions of the matrix, the way in which you calculate the determinant could vary. But basically what the determinant does, it is a matrices way of trying to identify the size of the matrix or the weight of the matrix. Okay. And so what we'll focus on here is the 2x2 matrices. And so given that we have some, let's say, matrix A here that has X, Y, Z, and W, then when we find the determinant of A, and this is one notation, det A, but we also do it like this to sort of say the absolute value. It sort of borrows that notation. And of course, the absolute value, or some people call it the modulus, it sort of has the same meaning of what is its weight or what is its size. Okay, how we do that is we could just multiply across, so x times w and minus z times y. And so I think I'm going to change these variables here to do something that's a little bit more traditional. So normally when you see this in a textbook, they'll do it like this, to where you just say it's A times D minus B times C. And so that's how we actually calculate the determinant of a 2x2 matrix. So here, if you notice, for our matrix, which has 7, 4 in the first row and 2, 6 in the second row, and this is 2, 6, not 26. So I want to make sure that we understand that. Let's get rid of that small thing there. So let's get rid of that. So now 2, 6, like that. Then of course that would be 7 times 6 minus 2 times 4. And of course that would be 42 minus 8. And of course that would be 34 as the result. And so that means here, when we do this, this will be 7 times 6 minus the 2 times 4. And of course that would be 42 minus 8, which is 34. And so that is how we calculate a simple determinant of a 2x2 matrix. All right, so for the second part here, it says that the value of this second order, and we're going to say determinant, is going to be 34. Okay? And of course, we took the determinant, so that's why we put second order determinant, and of course its value or its size is 34. Alright, so if we wanted to calculate the determinant of this next matrix, of course it would be the same kind of thing. So I'll go ahead and move down here, and we know that to calculate the determinant of this, we just do 9 times 8, which is 72, times 4 times 5, which is 20. And so that result would be 52. And that will be the size of that matrix. All right, so moving on to the next question, we'll take the determinant of this matrix. So there we will have a -1 times a -8 minus 4 times 16. And of course, negative times negative is positive. And we see here that this would be 64. And so, of course, if we did that, the answer to that would be a -50. Oops. That is not negative 58, that is a negative 56. Okay, and this is just to show you that we can have matrices whose determinant or size is negative. All right, so now we're going to calculate the value of this determinant. So let me make some more room here so that we can do that. All right, so we're going to do just like how we did last time, and we're just going to multiply top times bottom minus bottom times top. So we have 3/8 times 1/7 minus 5/8 times, or should I say 3/8 or 3/7 times 5/8. Let me do it in order. All right, so when we multiply this, we have 3 over 56 minus 15 over 56. And of course, 3 minus 15 is a negative 12 over 56. And so I think here we can reduce this because we know 12 is 4 times 3, and 56 should be 4 times 14. So we have a common factor of 1 there. So we have negative 3/14. That is what our determinant should be. And looks like I got a little something extra there I shouldn't have. All right,